Thank you very much, Igor. So you can go ahead. Thank you very much. Yeah.
Okay, so I want to start also thanking the organizers for giving me an opportunity to present our recent work on magnetic superconducting topological surface states on iron chalcogenide family, and for organizing this very nice series. So this work is a work of our Brookhaven Neutron Scattering group that was the first. The lead author is Yang Muli, who did the most of the hard work in this project, bringing it to fruition. So it started as a neutron scattering project where we did neutron scattering studies in collaboration with different members of our neutron scattering group on top, and with an excellent support of high-spec instrument team at Oak Ridge National Lab. Here on the bottom left, and then as on samples that were made in our neutron scattering group by Genda, Chedamir, and Jijunju. And as our work progressed, we realized that we need to comprehensively microscopically characterize our samples or small pieces of our neutron samples, and that was done at Brookhaven Center for Functional Nanomaterials in terms of chemical and resistance microcharacterizations in collaboration with Fernando Camino, and then the very comprehensive characterization using the micro-resolved RPES measurements in collaboration with Peter Johnson's group, in particular Nader Zakia performed a lot of measurements which were analyzed and systematized by Youngmu to obtain the results that I'm going to report to you here. All right, so the outline is such that I have a rather extensive introduction, which I hope to skip rather fast because it emphasizes the points that were raised by different speakers in the series, and in particular, the importance of strong electronic correlations that was emphasized by the previous speaker to set up the main problem that we have addressed in this work, which is the puzzle of inhomogeneous superconductivity and topological properties that have been observed in the iron chalcogenides recently by STM studies, and our resolution of that puzzle in the form of iron and tellurium composition controlled phase diagram of different magnetic superconducting and topological phases that we have discovered in this material series. All right, so iron chalcogenides, as everybody knows, are the simplest family of iron-based superconductors with layered structure. Here is another rendering of the structure from a DFT work, which sort of illustrates formation of bands via hybridization of iron 3D and tellurium 5p orbitals. And the band structure computed by DFT at a very early date, so in iron telluride, was very similar to the one in iron nictide materials, with a hole pocket at gamma point near Q equals 0 and an electron pocket at M point pi pi. And so here is a illustration of a brilliant zone with two pockets, and then there is a nesting between gamma and M points, which in the itinerant electron picture suggests a tendency to magnetic ordering at a wave vector pi pi. I know that there is nothing at x point pi 0, and nevertheless the parent state of iron chalcogenide superconductor family iron telluride has magnetic ordering at which occurs at exactly x point, which this is so-called double stripe ordering, which is difficult to explain in the simplistic itinerant electron picture based on the DFT calculation. On the other hand, the parent phases of nictide superconductors do show the single stripe, so-called magnetism with propagation vector pi pi corresponding to this M point, and that can be rationalized by nesting. Of course, when materials are doped towards superconductivity, the long-range order goes away, and in the doped compositions which are superconducting, the dynamical magnetism is persists in the form of dynamical fluctuating short-range correlated patterns, which nevertheless preserve the features of the electronic state observed in apparent phase. For example, the short-range version of the this single stripe order, whose real space version is illustrated on the bottom right, is that would be measured by Neutron scattering, is shown in the right middle panel with strong intensity at pi pi points here, while neutron scattering would show a pattern with stronger intensity at pi 0 points in a short-range dynamical version of double stripe magnetic order. All right, so the resolution of a puzzle of double stripe magnetism can be looked into in the strong correlations characteristic of these iron telluride or iron iron chalcogenide family. So these are very early calculations by DMFT. Which by Gabby Kotler's group, which show that indeed iron telluride is the most strongly correlated among all iron-based superconductors family, which leads to substantial renormalization of bandwidth or effective mass. But more importantly, it leads to a substantial decoherence, which can develop upon rising temperature to reasonably low values. For example, in iron telluride, DMFT predicted that a coherent band structure near the Fermi energy exists at low temperatures and gets substantially decohered at reasonably low temperatures of the order of 100 Kelvin and above. That was actually consistent with our earlier neutron scattering work, where we have observed a change in the total magnetic scattering that can be assigned to local moment fluctuations from local moments corresponding to spin 1 or 2 localized electrons at low temperatures to local moments of spin 3/2 or 3 localized electrons at high temperatures. So this is in agreement with 1 electron that gets coherent upon cooling, leaves its local moment localized state and goes into a conduction band. And this was consistent with the measured resistivity, which became more metallic, corresponding to appearance of conduction electrons, and decrease of magnetic susceptibility, illustrating decrease of magnetism, of local moment magnetism. We have later discovered that this transition is actually accompanied by formation of the bond order wave made of zigzag ferromagnetic chains. So this is a sort of orbital order that develops when electrons become coherent. This order, by the way, explains this double stripe magnetic order as the order of antiferromagnetically coupled ferromagnetic zigzag chains, similar to the situation in manganites. But the point I'm making is that the development of electronic coherence and cooling leads the way to development of electronic instabilities, such as formation of orbital order or of a superconductivity. So one needs electronic coherence in the first place to form superconducting state. Now, later studies by ARPAS, by the group of the previous speaker and Mingy in particular, have provided direct evidence of orbital selective band decoherence and strong renormalization effect in iron telluride selenide materials. So the bandwidths measured by ARPAS were much narrower than the bandwidths obtained in typical DFT calculations. In fact, the renormalization was orbital dependent and reached as much as order of magnitude for DXY bands. And it was also shown directly by Mingy that the coherence of DXY band goes away upon warming in qualitative agreement with the predictions of DMFT and with our observations of localization of one of the electrons. So the effects of strong correlations are extremely important and lead to decoherence of electronic band structure near the Fermi level in this material family. One way to sort of phenomenologically take into account these effects of electronic strong correlation in a DFT approach would be to make DFT calculations in a magnetically ordered state. And it was shown by Peter Johnson's group that one can, in principle, sort of rationalize the measured, ARPAS measured band structure near the Fermi level with, these are two bands near the Fermi level, alpha 1 and alpha 2 measured in iron tellurium 0.45, selenium 0.55 composition. So one can sort of get a good agreement between this band structure and the magnetic, the calculations of DFT calculations in the presence of magnetic order. But what they discovered is that it is also extremely important to take into account the spin-orbit coupling, which is strong on tellurium atom and is transferred onto principally DXZ, DYZ derived bands, alpha 1 and alpha 2, which are spin orbit split. So this is actually this was actually interpreted as very large spin orbit splitting of these two bands at the Fermi level. So I think this was one of the earliest demonstrations by ARPAS that spin orbit coupling is extremely important in these materials. It was also shown that this alpha 1 band, this is a bulk band that I will be talking about later in more details, is actually non-dispersive in the direction perpendicular to the AB plane, which actually also contradicts the simplistic DFT calculation, but that is just another failure of DFT. Oh, anyway, despite all these failures of DFT, several groups in around 2015, around the same time, came up with a DFT-based prediction that there is a band inversion in this iron tellurium selenide system for certain selenium-tellurium composition, near half, and there is a formation of a topological surface state related to this band inversion. Of course, some of the authors, in fact, were cognizant of the fact that correlations can significantly modify or negate this picture. In fact, in one of the papers, there was a DFT, DMFT calculation in an appendix showing that a decoherence of the bands develops. But nevertheless, the experimental verification, I mean, there were experiments conducted following these predictions, which indeed observed formation of this topological surface state, and it was in quantitative disagreement with the theory because theory predicted it to be way above the Fermi level, but luckily in experiment it was observed right near the Fermi level. So it was a disagreement which was very favorable for us. Now, in the presence of and that this is a topological surface state, of course, relies on the fact that there is a band inversion, and there were subsequent studies, and one of these studies was actually reported earlier in this nice seminar series by Kanigal. So Kanigal's group has indeed shown that this alpha 1 band does experience band inversion. It changes symmetry along gamma Z line, and that was shown by measuring intensity along gamma Z, and showing that that intensity varies. So anyway, there is a band inversion. There is also another study that showed directly band inversion in a series of monolayer films of iron tellurium selenide with different doping. So there is band inversion. In the presence of the superconductivity, and the superconductivity in the ARPAS shows up as this superconducting condensate peak split off the Fermi surface of the Fermi level by a superconducting gap. This is this bright flat feature here. So this is a measurement on the same series of materials also by Kanigal's group. And I'm showing here, showing this measurement here is because we will use this feature to quantify the presence of superconductivity in our sample, in our work. So in the presence of superconductivity, which can be quantified by the presence of the superconducting condensate peak, the other thing I want to mention, looking forward, is that you see that the superconducting condensate peak is extremely sensitive to the iron content. In fact, in this work, they mentioned that this change of the superconducting condensate peak occurs on decreasing iron content, but the change in Y, this iron content, was so small that they weren't even able to report numbers. So they just said it's bigger here and smaller there, but it was, I think, within 1%. Okay, so nevertheless, in the presence of this bulk superconductivity that can be evidenced by the superconducting condensate peak in ARPAS, the surface superconductivity can be induced, and in that surface superconducting state, topological superconductivity would host Majorana zero modes in the cores of the vortices on the surface of the superconductor. And those vortices and the presence of those Majorana bound states in the cores of topological vortices can be measured by using STM, and they show up as zero bias peaks, which were found experimentally and reported right following the report of the surface state itself. And so it would be a total end of the story, except that follow-up work reported that along with the topological vortices that hold the zero bias peak here, as a function. So this is intensity as a function of bias and the position in the vortex core. So you see this is a zero bias peak. There are also nearby vortices which do not show Majorana zero mode, and so there are trivial vortices corresponding to a regular non-topological superconductor. Now, another work actually mapped the distribution of trivial vortices, which are shown by white diamonds here on the and topological vortices with Majorana bound states, which are shown by red circles here on the surface of superconductor. So what was observed is that this topological surface superconductivity seemed to be strongly inhomogeneous. So it presented really a puzzle. Now, approximately at the same time, a report appeared showing that, again, by Josephson STM measurement of this iron tellurium selenide material with tellurium selenium composition of 0.55, 0.45. So the report appeared that showing that the superconductivity itself is strongly inhomogeneous in this material. So the panel B here shows distribution of the superfluid density, while below panel E is the inhomogeneous distribution of the superconducting gap measured by Josephson STM on the surface of this material. And in fact, the inhomogeneous superfluid density is also accompanied by inhomogeneous normal state resistance on the surface. So the superconducting properties of this material and the electronic properties seem to be substantially inhomogeneous as measured by STM. In fact, I want to mention that earlier, very similar, in my view, the electronic inhomogeneity of the superconducting state was observed in viscous cuprate superconductor by the same Josephson STM. So this panel C shows the variation of the superconducting gap as measured by Josephson STM on the surface of viscous sample. In that case, it was explained by virtue of the proximity of that material to the electronic nematic transition, which can be understood as a quasi-two-dimensional, which can be described by quasi-two-dimensional random field Ising model, which shows a large critical range where two different phases coexist, and theoretical simulation of this observed inhomogeneous electronic state found that it is consistent with the random distribution of these Ising domains, which result from the proximity of the material to the phase transition line. Okay, but in the iron tellurium selenide near 0.5 doping, it would look that the material is far from the transition line between the parent state, where magnetism is double striped with neutron magnetic scattering looking like this, to a magnetism typical of a superconducting phase, which shows a single stripe type magnetism, which peaks at near M point. And so the question is, why would the superconductivity and topological superconductivity be inhomogeneous? An answer, or a possible answer to that, lies in a well-known sensitivity of this family of materials to iron composition. So it has been known for a while, if we look on the panel on the left, this is from Vienas et al., that in the iron, in order to have a well-developed bulk superconductivity at compositions between 0.3 and 0.5 selenium doping, you need an iron deficient materials in nearly nominal iron, for nearly nominal iron content, even for selenium doping of 0.45, material can be non-superconducting. So iron represents a substantial handle on the appearance or disappearance of superconductivity in the material. However, there are many ways of destroying superconductivity. You can have magnetic scattering of some interstitial irons. You can have a disorder, potential scattering, or there can be a possibility that, in fact, iron tunes transition between two competing electronic phases. And while, in fact, it looks exotic, it is exactly the possibility that I will try to convince you is the case here. All right, so in order to understand what's happening, we took two big samples with slightly different iron composition, and measured magnetic Neutron scattering on those. So these are shown on two right panels here. So the middle panel shows magnetic Neutron scattering pattern measured on sample A, which was prepared by Gendago and our group, with having slightly more iron than well superconducting sample B. So we checked that sample A is non-superconducting not only by measuring, and sample B is superconducting, not only by measuring a magnetic susceptibility on a small sample, but these measurements were performed using polarized neutron scattering, which has unique sensitivity to the appearance of superconductivity in the bulk sample. If sample becomes superconducting and undergoes a transition in a small magnetic field, which we use to guide neutron's polarization, the neutron beam becomes depolarized. So from that, we actually know that a big piece that we measured of type A, this one, is non-superconducting, causes no depolarization of neutron beam, while this big chunk is superconducting. And so in this measurement, we have what we have observed, that a non-superconducting sample demonstrate magnetic scattering pattern dramatically different from a superconducting sample. This one is typical of a single stripe, of a double stripe magnetic correlations, while the superconducting material, sample B, shows a pattern typical of single stripe magnetic correlations. And the non-superconducting sample A showed a pattern that was very similar to the one that we measured previously in weakly sulfur-doped, sulfur-substituted material. So what that shows is that apparently there are just two different phases electronically, the one from which superconductivity can appear and the one from which superconductivity cannot appear. All right, and in order to confirm that, we have measured the non-superconducting sample at high temperature, 300 Kelvin, and the scattering is essentially the same. And we measured the superconducting sample at a temperature above the superconducting transition, and the scattering pattern is also the same as below. So what this tells us is that we observe change between the two samples, A and B, non-superconducting A and superconducting B, which is characteristic of a parent non-superconducting state. So that something happens to a parent electronic state that dramatically changes the local magnetic correlations with slightly changing amount of iron. So we were, next question was, is it really a small change in the amount of iron? So we need to quantify the real composition of our materials and to measure their electronic properties. And so we did that by choosing a number of representative small pieces from each of the two samples, 9 in total, 5 from one, 4 from another. Each little crystal was subjected to thorough analysis of its elemental composition and electronic properties by making a 100 by 100 micron grid on the surface of that crystal, and then measuring the composition, the elemental composition in each cell of that grid using EDS, measuring the electrical resistance on that little element of the grid by using the microprobe at nanocenter, and by measuring the local electronic ARPAS spectrum by using the micron resolved ARPAS. And so we observed that there are 3 types of regions, just 3 types of spots on which different ARPAS spectra are observed. We either observe an ARPAS spectra, such as in this violet region, which contains bulk band, a surface state, this bright yellow spot, and a superconducting condensate peak. There are other regions, like one marked by green spot here, where the bulk band is observed and the superconducting condensate peak is observed, but no topological surface state is observed. And yet there are other regions, like the one that's shown here by yellow, where a totally incoherent band structure is observed. In other words, no coherent features can be easily identified. In fact, I understand that in many previous studies, in many previous ARPAS studies, when such spectrum would be seen, it would often be dismissed as a bad spot. Now, we have measured all spots on the samples, and so if 30% of your spots are bad spots, and you can correlate the behavior of the spectra in those bad spots with their chemical composition and their resistivity, that would tell you something, and that's exactly what we did. So it turned out that these type of bad spots typically have higher room temperature resistivity. Also, upon cooling, they show non-superconducting behavior. And while the other two spots have lower resistivity, the ones that have coherent features in the ARPANET spectrum, lower resistivity, as well as they show the superconducting transition on cooling. So the first question, of course, the main question we asked based on the neutron scattering results was what is the composition of our samples? And so what we did, so what this represents is a histogram of composition measured on these humongous compositional distribution measured on these humongous grids on 9 samples. And what we see is that indeed the main difference between sample A, which is a non-superconducting, and sample B, which is superconductor, is that sample B has really slightly deficient average iron content, while sample A is nearly stoichiometric, but probably maybe 0.5% more iron than stoichiometrically allowed. And then the iron and tellurium compositions are very similar, near the nominal 0.55, 0.45 proportion. And so if we plot the probability of encountering a certain composition in a sample as a function of iron on the x-axis and tellurium on the y-axis, then sample A, non-superconducting one lies here, and sample B, the superconducting one, lies here. And I will show what this line is. This is a line of a transition as we have determined between the superconducting phase and the non-superconducting phase. Now, how do we determine this line? We determine this line by analyzing the ARPA spectra that were measured. So each spectrum was modeled by fitting to a spectrum containing 3 features: the bulk band feature, the topological surface state feature, and the superconducting condensate feature. So the intensities of these 3 features were fitted for each spectrum, and the typical, so this is a color plot of the typical fit at 5 Kelvin. This is a color plot of the typical fit at 19 Kelvin above the superconducting transition temperature. This is just to show that there is a gap in a topological surface state that opens upon entering the superconducting state. This is something that was recently reported by Peter Johnson's group in this paper here. The main point I wanted to emphasize here is that our model gives a very accurate account of all the features that are observed in the spectrum. And so we used it to quantify the presence of a certain feature, quantifying the existence of a certain electronic state under that spot on a sample. And so here what we do, we represent the intensity of each of the features as a function of iron content and tellurium content. So this makes us this forms a sort of a phase diagram. So panel A shows the intensity of the superconducting condensate feature, and we see that iron deficient spots have stronger intensity or strong intensity of superconducting condensate feature, while it fades in the region of phase diagram, which is iron rich. Similarly, the coherent bulk band, its intensity is strong in the iron deficient region, and then it fades in the region where iron content is higher. And so these are sort of those bad spots where we don't see basically, among these are those bad spots where we don't see basically bulk band. Now, in the same phase diagram, we can represent the resistance that we have measured using the microprobe. And what we see is that iron deficient region has more conductive surface than the iron rich region. And it correlates perfectly with the intensity of the bulk band and the intensity of the superconducting condensate peak. So based on these 3 measurements, we have refined, based on the 50% threshold in the corresponding variation of the corresponding property, we have refined this phase boundary between the resistive, incoherent, non-superconducting state at higher iron content and the conductive, coherent electronically state that develops superconductivity. Now, it is only in the superconducting phase, but only at a high tellurium content that the topological surface state feature is observed. So you see, this is the intensity of the topological surface state feature. We see that there is a separate region in the superconducting part of the phase diagram, which also hosts topological superconductivity. The Dirac gap that opens in this phase actually closes at the boundary of the at the phase boundaries. So the topological superconductivity arises together with the Dirac gap. We can make maps of various quantities that we have measured. In particular, this is a map of the different phases on the that we have observed on the surface of this of a particular sample. So you see the dark violet, the dark blue or dark violet are spots where topological surface state and superconductivity are measured. The greenish ones are superconductivity that is a trivial superconductivity, and yellow are the non-superconducting spots with incoherent electronic bands. So to conclude, we have been able to construct a phase diagram which shows that at a higher iron content, an electronic state realizes, which is where the band structure near Fermi level is incoherent. It is characterized by a double stripe type magnetic correlations, which are most likely arising from strong correlation effects. And upon lowering temperature, no superconductivity develops and correspondingly no topological surface state. At a lower iron content, we have a transition into a phase that does have coherent bulk band, which does develop coherent superconducting peak below below superconducting transition temperature, and at higher tellurium concentrations, this phase also hosts the topological surface state. So iron stoichiometry controls magnetism, coherence, electronic coherence, and electronic transport, and as electronic coherence develops, the superconductivity develops upon lowering temperature in a way similar to how the orbital ordering develops in iron telluride upon developing of electronic coherence. And the tellurium concentration drives the topological surface state, and when the increase of the spin-orbit coupling of tellurium gives rise to topological surface state. Now, the puzzle of the puzzle that we were the puzzle of inhomogeneous superconducting and topological states is basically answered by the position of these samples. And I need to mention something I forgot to mention, that samples used in most of those studies that have been reporting the topological surface state and Majorana modes, many of those samples, if not most, came from the same source, that we used in our study. So they were made by Gendagu. And so the superconducting samples, they were all representative of this B sample. And what we see is that it's right at the boundary of the phase transition line between a trivial and topological state. Both samples are also close to the transition line between the non-superconducting and superconducting state. And so, in fact, even if samples would have been ideally stoichiometric, because that stoichiometry puts them in the proximity of phase transition lines, the fluctuations of electronic fluctuations that are intrinsic to those phase transition lines would be unavoidable. So the key to harnessing these topological surface state and superconductivity would be to try making a sample down here in the region of phase diagram, which is farther away from the phase transition lines. All right, thank you very much for your attention.
Thank you very much, Igor. It's a very beautiful experiment. I'm going to take advantage of my position to ask you first question, if that's okay. So for the slide where you show that for where you measure the low energy magnetic excitations for the three different, so the yes, this one. Mm-hmm. If you were to measure the rightmost sample with a fewer iron excess iron at high temperature, what would you see? Would you see the same pattern?
Very good question. Yes, it does develop incoherence, and the pattern changes dramatically in this direction.
Okay, great. That would be exactly consistent with our
Yes,
Is on the same.
I have that measurement. It's just not. I'm working. We are working on it. Yes,
Okay, thank
you're
you.
absolutely right.
The second question is, if I can ask, so you only show the band dispersions around the gamma point. Do you also have information around the endpoint for this?
The ARPAS. This is a laser ARPAS that we have here in the building. So it only has a very small. In fact, we were beaten by the referee who were saying, you don't have an access to this other band that goes, at larger Q, and we were. I mean, the access to that band in a way is provided by us seeing the superconducting peak, which actually sort of comes from that band.
Okay, I see. Thank you very much.
Mm-hmm.
I think it was Pengcheng first.
Yeah. So yeah, very nice talk, Igor. Yeah, so do you know what happened to the excess iron? I mean, do you know the positions of these?
Sorry.
I mean, for the non-superconducting samples, right? I mean, you have a completely different magnetic spectra, right? How much more excess iron you have?
Pengcheng, yes. So you see, the thing that I do really find absolutely stunning is that, firstly, there is so little. So this is a histogram of iron distribution, right? So the superconducting sample, it's slightly less homogeneous, as you can see, but the average average iron composition is probably 0.98, right? So first of all, it's iron deficient. Of course, we are not 100% sure that it's 0.98. It might be 1.01. I mean, not 1 point, maybe 1. The absolute accuracy of our measurement, its EDS, is not so great. The relative accuracy is very good. So what we can tell you for sure is that the composition of this one is just 3% different from the composition of this one. Now, to that accuracy, determining from a diffraction experiment either vacancies or interstitials, on the level of 1% is, I don't think it is feasible. So we don't know. The answer is there is so little difference in iron that we don't really know where it is.
I see. But do you have diffuse? Do you have a neutron diffuse scattering measurement? I mean, to show that maybe on Corelli or something?
I mean, we have. There is main. Okay, so. As I've just said, the amount of extra iron is so small that, of course, I have the measurement of. I mean, we have these. We have measured the full, volume with unpolarized as well as polarized neutrons. So diffuse scattering is totally dominated by magnetic scattering. So there is no structural diffuse scattering that can be seen to be associated with structural, disorder and imperfections.
Okay, thank you.
I think it was Christoph next.
Yeah, very nice talk. I was wondering, what is the difference in annealing, or how did you prepare samples A and B? Was it tellurium vapor?
Sorry, well, I didn't.
How did you prepare the difference between A and B, sample A and B? Is it different annealing times?
This was really sort of low tech, just putting in a little bit, varying the input composition of the input material, iron and tellurium and selenium.
I mean, usually these samples, they have excess iron, right?
Well,
you have to anneal them to get rid of the excess iron.
No. Okay, so no. So the sample B which is well superconducting and turned out to be slightly iron deficient according to our measurements, was just as made. So it's just again the optimized initial composition of. I mean, they did some research to optimize the composition such that a well superconducting samples can be grown. So we did not do any post-processing to this sample.
Okay, and the second question is, what are the TCs, and did you measure heat capacity of these samples?
We did not measure heat capacity. No, we did measure, so on the small pieces of these samples, we measured the magnetic susceptibility and all the other measurements that I have just reported. The big samples were measured by neutron scattering. And as I mentioned, I mean, this was actually, I was always have this question, when you measure a neutron scattering sample and you say, this is a superconducting sample and this is non-superconducting sample, but how do you know? Now I'm telling you, I know for 100%, this is a superconducting and this is non-superconducting.
heat capacity would be another method. Huh?
Yes. Oh, you know what? I can show you something. I think I have. Oops. I have. Oh, here it is. So this is a Neutron scattering measurement of a magnetic field, sort of a magnetic field trapped in a sample upon cooling. So this is a flipping ratio that measures how how neutron beam is depolarized as a function of temperature of the sample. And you see this beam is well polarized here above 14 Kelvin, and then boom, it goes down.
So TC is 14 Kelvin.
Right. Yeah. That basically is a measurement of a transition temperature on a bulk sample by neutron scattering. Very expensive measurement, but it was not the goal of the experiment.
Okay. But it doesn't tell you the volume fraction, though.
Well, this is a difficult question. I truly cannot, but I can estimate. And I did an estimate, and it turned out I mean, 90% plus minus 20. Let's say it this way.
Okay.
Okay, thanks. Yeah.
Sorry. So I guess Jamil?
Yeah, so Igor, I have a quick comment about something that you said on the site, which was about 100% FeTe. You seem to suggest that around 60 Kelvin or something like that, that the XY states develop coherence. So my comment is that I don't think that's right. I think all the indications are that the XY states stay incoherent all the time.
I did not say that it's specifically XY state.
But what I thought that's what you were suggesting.
No. Sorry, I said two different things. I said that in parent material, we have seen the development of we have seen the change in local moment here, which corresponds to, which can be understood as development of the band of the coherence in the band structure near Fermi level. Which bands or which orbitals are involved, we have no access by use from these measurements. Now, the other thing I said, I think I referred properly. Mingi should correct me if I was wrong. That was describing her measurement on iron, tellurium, selenium. I think near half doped material.
Specifically focused on FeT.
Right. So there, I think they showed that it is DXY band that loses coherence.
Well, I don't think there's any establishment of coherence at low temperatures, but we can discuss later. It was a comment.
I thought that that's something that ARPA's data have shown directly.
FeTe, it's fully localized.
No, not in FeTe, in FeTe.5 SE.5.
No, I'm focused on FeT. My comment was about FeTe.
Right. So on FeTe, I mean, this is a picture that shows that there is an electronic coherence that is being established, but what bands are involved, we do not really, I cannot really say.
All the orbitals have been looked at, and there's no evidence for any of the orbitals becoming coherent at that temperature.
Well, maybe there are some other explanations, but it's clear that the amount of magnetic scattering and the resistivity and the susceptibility are all correlated, and it's all correlated with the development of this.
It's a very interesting neutron measurement. I'm just, well, the comment was very specific about electronic.
Yeah, so my way of rationalizing it is by comparing with the Gabi-Kotlar's calculations, which show that electronic coherence is developing here. But if you say that there are other ways, I mean, I'm open.
The comment is that experimentally, there's no indication of establishing coherence in any of the orbitals at that temperature.
At low temperature. No, coherence is established at low temperature.
At any temperature.
So experimentally, there is a change of resistivity behavior from bad metal where resistivity increases with lowering temperature to a good metal where resistivity decreases with lowering temperature.
I don't have a comment on that. I'm just saying that from single electron excitation spectrum, there's no establishment of coherence.
Well, maybe there are alternative explanations of this. I don't know. I mean, That was our way of rationalizing this observation experimental.
Henri, do you have another question? Or?
Yeah, well, I have a simple one. I like the neutron scattering data, but I wonder when you are comparing to ARPES data, is it safe to compare bulk measurements to surface measurements? In some sense, how do you know that the surface would have similar compositions, etc.? This seems a little bit dangerous for me.
Okay, the question is, in our view, the question is twofold. One, and that is something that Peter Johnson sort of taught me to say, and I truly believe that this is true. ARPES is a technique that is sensitive to both surface features and bulk features. So
not the bulk of the sample. No, it's not the bulk of the sample. It's still right on the.
No. You see, what that says is that if there is a bulk band in the sample, you can also measure it on the surface.
Of course.
Yes, so that is one. The other is how representative is this measurement of a particular surface of this particular sample of a bulk. Now, if we take, in this case, we measured 2,000 spots. So we basically take 2,000 different surfaces from the bulk.
Mm-hmm.
And we see a clear correlation between our measurements. In that way, we believe that just statistically, these are representative of the bulk.
It's statistical, but you are not measuring the same spot with neutron scattering and ARPES.
No, but I'm measuring the average of all the spots measured by ARPES with neutron scattering.
You're comparing the histograms of both. Okay.
Right, yes, exactly. But we only have three, but you see, we are aided by the fact that we only have 3 types of ARPES patterns. And they can be correlated to 2 types and only 2 types of neutron scattering measurements.
Well, one has to look in detail to try to see how these correlations are really, but okay, I accept what you say.
Any other questions?
Thank you very much.
If not, I suppose we can close the session today. Thank you both, Igor and Zach, for leaving earlier. Thank you both very much for your time.
Yeah, very, very nice time.
Yeah. And
thank
I guess
you. Bye-bye.
Thank you, Igor. Yeah. Thank you, Zach.
Thank you.
Thank you all.
Bye-bye.
Yeah, good to see everybody.
Hello. Bye-bye.
Good to see you.